All right, hello people. I'm going to go through these fast, and if you are watching this, you can slow it down, speed it up, pause whenever I'm going to go through a problem or anything like that, but I don't want the video to last forever, so here we go. So we're going to look at mechanical energy. There are three types we're going to look at, and we have kinetic energy. All right, and that is the energy of motion. You should have been able to gather that from the skate park lab, where the bar graph was at its maximum whenever it was moving the fastest. There is gravitational energy. Oh, potential, and we'll just say potential energy first. Potential energy, and this is stored energy. And there are two types of stored energy. We are going to have gravitational, and we're going to have spring or elastic energy. Okay, so kinetic energy is related to the speed of an object. So the mathematical relationship there is the kinetic energy is equal to 1/2 the mass of the object times the velocity squared. Now we're going to look at the units here too and figure out what energy's units are. The way we figure that out, we look at the units of what we're doing over here. Mass is in kilograms, velocity is in meters per second, but it's being squared, so it's meters squared over second squared. So a kilogram times a meter squared over a second squared is the unit of energy, but they named this after a guy with the last name joules, right, or joule. All right, so this kilogram times a meter per second square, meter squared over a second squared is the same value as a joule. Now we looked at other types of units that were called something else. The Newton. The Newton was a kilogram times a meter per second squared. This one has that extra meter on top. All right, so stored energy. Gravitational potential energy is related to the height of the object, and you should have saw the bar graph for the skate park. The skateboarder was the highest whenever they were the highest, all right, at mgh. Let's look at the units again. We have mass, kilograms. We have g, meters per second squared. Hey, there's that kilogram times the meters per second squared that we were just talking about is a Newton. All right, so I'll write that over here too, so it's going to equal a Newton. So kilogram meters per second squared is also equal to a Newton. And then we have the height, which is in meters, right? So kilograms, meters per second squared, meters, all multiplied together. This is going to equal a kilogram times a meter squared over a second squared, which is what we had over here, which shows that it is also a joule. Now let's do that extra jump here. That is a Newton, and then this is a times a meter, so it's a Newton times a meter as well, equals a joule. All right, for the spring potential energy, it'll still be PE spring, and that's going to be equal to 1/2 kx squared. All right, so let's define what these things are. Well, actually, let's do this in a second. Let's do the units first. I'll explain what K is, but the units for K are a Newton per meter, and that will make a little bit more sense when I define what it is. All right, and then an X is the spring stretch or compression distance, so that's going to be a distance to meters, and it's squared, so we get the squared there. All right, now this is going to equal a joule, but how does it relate to these other things? Hey, there's this meter here. That cancels out one of those meters here, which equals a Newton times a meter, which relates to what we just saw up here. So the units do work out, even though you have very different variables in there. All right, so K is the spring constant, sometimes called the force constant. It is how much force is needed to stretch or compress, stretch or compress a spring 1 meter. All right, its units are newtons per meter. Newton per meter. So if I had a spring constant of 100 newtons per meter, that would mean in order for me to squash that spring 1 meter, I would have to exert 100 newtons. Sorry, that was out of frame. Okay, so units, newtons per meter, 100 newton per meters, 100 newtons it takes to stretch or compress a spring 1 meter. All right, let's look at the next thing, which is called total mechanical energy. Total mechanical energy. Those are the 3 types of mechanical energies. So the total mechanical energy is the sum of the energies that exist at any point. Some of the mechanical energies, the 3 that we just talked about. Mechanical. So mechanical energy is just capital E, and then we had the other types, which were potential energy of gravity, potential energy of a spring, and kinetic energy. So the total mechanical energy is the sum of the other 3 forms of energy. Now, we're never going to have all 3 of them exist at a point. All right, you will either have 1 or 2 at a single location through the object's change in motion. All right, now the next thing, we're going to be applying these things to the conservation of energy. There are problems that are in the basic assignment, basic energy problems, where you're just using those equations, where it might just ask, what is the potential energy of an object? MGH. What is the energy put into an arrow if it was all spring energy at first? So those 3 equations and the basic ideas that you should have gotten from the Ed Puzzle and the Energy Skate Park are going to be helpful for the first assignment. The conservation of energy here is going to be helpful for, guess what, the conservation of energy assignment. And I'm sure in chemistry they talk about the conservation of energy. It just says that energy cannot be created or destroyed. Energy. Can only be transferred from one form to another. Why do I feel like that's wrong? Transfer, it doesn't matter. Transferred from one form to another. And we're going to look at how mechanical energies transform from one to another. Okay? To save some time, what I did in my first class is I looked at just some scenarios without numbers, and then we went through some problems with numbers. Let's do the same thing. So here I have we'll have rock being held at this point. We'll say it's point A, and it is some height above the ground, and it is being held there at rest. All right, so it's you holding a big rock up, doesn't matter. And then you drop it, and we know it speeds up, and then it hits the ground at its fastest speed. And we'll say that that's at point B. Now, we look at the energy at one point, point A. So the energy at point A, the total mechanical energy at point A, due to the conservation of energy, has to be equal to the total mechanical energy at point B. That's the idea of energy conservation. Boom. You're going to have energy at one point equal to the energy at any other point. Then you ask yourself 3 questions in order to write the next line in this energy relationship. Because remember, you have 3 different forms, So you're basically trying to identify which of those forms exist at that location. So you look at point A, all right, and you ask yourself, does it have a height? Yes, it is above the ground. And we are saying that this is where our zero line is. Usually you try to make it at the lowest point, not always, but that makes your life a lot easier because that makes the energy at the very bottom there, right, not potential. It has zero potential there. So only potential here. I'm going to write it out long ways here and write it out as the potential energy due to gravity at point A. And the second question is it moving? No, you're holding it at rest. So there's no kinetic energy. Is there a spring compressed or stretched at that location? No. So there's only one form of energy that you said yes to at point A. At the very bottom, does it have a height? No. Is it moving? Yes, it is the moment it strikes, the striking velocity that it hits the ground at. So yes, it is moving. It has kinetic energy at point B. Is there a spring compressed or stretched there? No. So there's only one form of energy, which is the kinetic. Now, there's different things that we can solve for. Usually we can solve for either how high was it dropped so that it hits at that speed, or how fast did it hit there. Let's solve for what is the speed that it hits the ground at. Okay, so now we have to make sure that we get V into this relationship. Well, we know what potential energy due to gravity is. That's mgh, and I'm using little h, so I'm using little h. Kinetic energy at the bottom is equal to 1/2 the mass. These are the same masses because it's the same object, and the velocity at point B squared. All right. Now, what's nice, whenever there is no spring, masses cancel. Mass doesn't matter. We dropped different masses before and saw that they hit the ground at the same time, which means they changed their rate of speed at the same, so they ended up at the same speed at the end, no matter what their mass was. Mass doesn't matter. All right, solve it for VB. Just get that 1/2 over to here, so you have 2GH equals VB squared. Square root it, then you get what VB is equal to, and I think that if you understood conservation of energy law, energy here equals energy here. What forms are? Does it have a height? Is it moving? Is there a spring? Okay, write the ones down that you say yes for. Use the equation that is equal to those forms of energy. Solve for the thing that you want. Algebra is easy. All right, so that's the first example that we looked at to just try to see how everything goes together. Let's look at another one. Let's put a spring in there. All right, so here we have a surface. Here's a spring. Put a block at the end of it. Usually, if the block is sitting on the spring, take the block away, we don't push on the spring would relax, and maybe it'll start like somewhere right here. All right, so what we're going to do is we're going to push that block back a certain distance here, and what we're trying to do is launch it across the table. So at some point later, it'll be over here, and it will be moving with some speed that we don't know. All right. So there's, again, two different things that they would really be able to ask us. How far must we compress the spring to reach this speed, or what is the speed if we compressed it this amount? So it's one way or the other. We'll call this point A, and anytime after, point B. The energy at point A has to equal the energy at point B. We look at point A. Is it moving? No. Does it have a height? No. We can decide that that's the lowest point and it's not going to change, so let's make it easier on ourselves. No height. Is there a spring compressed or stretched? Yes. So we have spring energy. At the end here, does it have a height? No. Is there a spring compressed or stretched at that location? No. Is it moving? Yes. We have kinetic energy. All right, so that is the spring energy here. We know that we have an equation for that, and that's 1/2 kx squared. Here we have kinetic. We know that that is 1/2 mv squared. Then if we try to do that solution here, yay, at least we can cancel out those halves, but mass is not in here. So when it's a spring, mass matters. That's kind of fun. Mass matters. Because matter has mass. I don't know. All right. You can't cancel out mass if there's a spring. If there's no spring, mass cancels. All right. So I already wrote V equals question mark, so you would just do the same algebra, moves, whatever it is, divide both sides by mass. Hey, it doesn't cancel. So V squared is equal to kx squared over m square rooted, and you can get whatever the speed was, or work backwards and solve for x instead. Let's just show that real quick. Instead of dividing by mass, we just divide by k. You have x squared is equal to mv squared over divide by k, and then square root it. I mean, very similar solution depending on which one you have to solve for. Okay, so those are the two scenarios that we went through without numbers. So let's try a problem with numbers. All right, so now if you want to try this on your own, pause the video right now. I need some different markers. Let's get some. All right, so if you wrote down the problem, good. If you don't like writing down the problem, if you draw the picture and label everything clearly, like here, you say, hey, this mass, oh, that doesn't show up. Let's get a different one. Let's try green, since I have green there. Mass is equal to 1.5 kilograms, and label that out. And the height, hey, we don't know, so let's question mark that. And it tells us that we have a speed here that's equal to 5 meters per second. So we have all of the information written down on our diagram. You can probably figure out what we want to solve for. I really wish that this stuff would show up a little better. That's a little bit better. Okay, so we can pick point A. I'm going to say it's point A down there, and point B up here. And I know that the energy at point A has to equal the energy at point B. All right, so this thing is just sliding. We don't know why it's sliding, but it is. It's sliding along the surface, starts to go up this hill, and we know that as it goes up, it slows down, and eventually it stops. We want to know how high does it go when it stops. All right, at point A, is it moving? Yes. So we have kinetic energy. We can go right to 1/2 mv squared if we want to, and that's the speed at point A. Does it have a height? It could, but let's make the bottom, the lowest point where our zero line is, our zero potential. So it has no height. And then is there a spring compressed or stretch at that point? No, there is not. There is only kinetic energy at point A. At point B, if it goes up and stops, is it moving? No. Does it have a height? Yes. Is there a spring there? No. You have one form of energy at point B. They are equal to each other. Hey, there's no spring. What happens? Those masses disappear, and you can solve for whatever it's asking for at this point in time. Well, that's showing up good. Let's continue there. I want height. All right, so a 1/2 V squared divided by G, and if you know your algebra rules, VA squared over 2G is what H is equal to. And if you plug in those numbers, again, pause the video, make sure you can use your calculator correctly, you should get a height of that many meters. And that is how you do that type of problem. So now we're going to jump into the next type. With a spring now. And we know that the mass is not going to cancel. Again, you can draw out the picture, read the information. We know that the mass here is 0.5 kilograms. We know that it is released from rest, so that the speed here is 0. I'll call that point A. And what's going to happen is it's going to slide down, it's going to hit that spring. Spring is going to go back and stop the block. All right, and we know the spring constant's right there. So you can, instead of writing out the whole problem, just write out that the spring constant next to the spring is that. And how far does the spring compress? Equals question mark. Hey, we have to know how high that is. All right, well, I didn't choose the height. I'm just going to make one up. Let's choose 5 meters. All right, now we set up the problem. We have the energy at point A is equal to the energy at point B. We ask ourselves 3 questions. This thing keeps pausing and like jumping, so there may be a point in the video where my voice speeds up or slows down. We'll see what happens. All right, the energy at point A. Is there a height? Yes. mg h at A. Is it moving? No, it says it's at rest. Is there a spring there? No. So there's only one form of energy at point A. At point B, it slows down to a stop, so it's not moving. It's at the lowest point, so it has no height. The spring compresses there, so it has spring energy. And our job is to figure out what X is. Do your algebra. You change my color here. All right, want X by itself. All right, this isn't, you can't get rid of anything. So we multiply by 2, 2mg times h at A, and divide by k, and that's going to equal x squared. And then I'm going to square root that, and I get that relationship right there. And since I did not have the mass there, I actually have to plug this stuff in. And if you're getting really good at your calculator, you can plug this all in at once. You can do second square root, and it's all in parentheses there. However, I have a lot of, it doesn't matter. There's no addition or subtraction here, and there's only one thing on the bottom. So it really doesn't matter even the order in which you multiply and divide. So you have 2 times the mass is 0.5, 0.5 times 9.8 times the height. I made that up to be 5. And then divide it by the k constant, which is 150. And if I did that right, you should get, not done. It was 0.57, all right, and I didn't square root it. My calculator shut off. It's the square root of 0.57. And when you do that, you'll get units of meters. Fantastic. All right, so that's that next problem. We did one more problem. Let's look at that. All right, roller coaster type of thing where blocks coming down the starting hill of a roller coaster. At that point, basically, it drops you off almost at rest. It's so slow at the very top of that hill. And then gravity brings you all the way through the rest of that roller coaster. So this thing is going to slide down, reach the bottom. We are interested in figuring out how fast it's moving at the bottom. Then it's going to go up this second hill. It's going to reach point C. And we're curious to know how fast it's moving at point C. All right. Got some information here. It says that this is 80 meters up at that point. There is no mass here. Don't worry about that. We already know that since there's no spring, the mass is going to cancel out. At point B, that's written down here, it says that point C is on a hill that's 35 meters high. So I'm going to come up here and I'm going to write that in there, right there. And I think if you wrote all that out, drew that out, and labeled it correctly, you wouldn't even really need the words here. But let's go ahead. How fast is moving at point B? So we look at point A. The energy at point A has to equal the energy at point B. At the top, is it moving? No. Does it have a height? Yes. And there's no spring. So this is just mg, and I used a big H there to differentiate from this hill right there. At point B, does it have a height? No, it's at the lowest point. There's no spring. Is it moving? Yes, it is. It's moving its fastest at the lowest point. So you have that, and there you go. The mass cancels. V is equal to the square root multiplied by 2, 2g, big H, and you should get an answer that is 39.6 meters per second. Now, what we know is the speed at point C is going to be less than that. So if we get a number bigger than that, we know one of those two is wrong. So what we do know here is that there's energy at A, and that we set that equal to the energy at B. Well, they're also equal to the energy at C. The total is equal at every single location. We want to add another point, point D. All right, then that's going to be equal at point D. All right, point A and a half. I don't know, it's going to be equal at point A and a half. All right, so at every single location, the total mechanical energies are equal to each other. So we can pick any point. We can set the energy at A equal to C, or we can set the energy at B equal to C. Your decision. I'm setting the energy at A equal to the energy at C. The energy at A was just that potential energy, which is mgh. At point C, does it have a height? Yes. Is it moving? Yes, because you know from the energy skate park that if you let an object go at rest here, guess where it's going to end up? At the same point so that it stops, because the energy at point A has to equal the energy at point B. The energy here is mgh. It's going to have to equal mgh. Since m and g don't change, the h has to be the same. Here the h is different, so it has to be moving. So it's moving, plus it has a height. There you go. We have two forms of energy on this side. There's no spring. You won't have all three at the same time. All right, now we manipulate that for what we want. It is VC. Oh, there's no spring. Let's get rid of that mass. Okay, so I'm going to leave this here. I have GH. I'm going to subtract that over. Minus G little h is equal to 1/2. M already canceled. VC squared. All right, and just multiply this thing by 2, but I have to multiply everything. So there's two ways you can look at it. There's a G in both of them. You can factor the G out, and then you're multiplying everything by 2 anyway. So you can get 2 times G, and then you subtract the heights. It's the difference in the heights that determine how fast the object is going to be moving there. It's very similar to this. Look, 2gh minus 0. Why? Because we were at 0 height. Now this is 2gh minus other h, because we're just going from here down to that height. All right, so we only need that amount of a drop there. All right, so you do that. Let's plug in those things. We had 80 meters at the top. We somehow it just turned back on. Minus 35. That's the h, big H minus little h, and multiply that number by 2 times g. And nope. I just got to square it. Square root both sides. And if I do that, let's see if I get the right answer. Should be less than 39.6. I got 29.7. I feel confident in that answer. And that is the last example that I went through for today's lecture. If you have questions, please write them down and ask them later. If not, there is a problem set that is on Canvas that practices conservation of energy problems. There's 5 problems, 10 points total. I think you can handle it.